Hi, I'm CS, the oscilloscope product manager of Rohde and Schwarz in Asia. Our today's topic is EMI analysis on power supply design. As you can see in front of me, we have prepared a few DUT for some demo as well. Today, we will learn about some general idea on EMC testing. What are those standards and limits, and try to understand EMC challenges specific to power electronic design. Then we will talk about some basic EMC debugging process and what tools are suitable for the measurements. Lastly, we will have some case study and a few hands-on to try on. What is EMC? In simple terms, it refers to electromagnetic compliance, which include interference as well as subsistence to electromagnetic noise. In EMI, we are concerned about the device under test or DUT are emitting noise both over the air as radiation as well as conducted as voltage or power disturbance. In EMS, the concern is more on the DUT immunity towards radiated or conducted disturbances. EMC is generally governed by ISO, IEC, and CISPR standard. Different countries may define different requirements that are specific to their region, such as US would be the FCC, and in China would be 国标, EU have CANELEC standards, and India has BIS requirement. Within CISPR, there are many subcommittees that work on different focus topics. For example, CISPR-A works on general measurement standards, while CISPR-F focuses on standards related to household appliances like CISPR-14 and 15. Hence, within the subcommittee, they would publish different CISPR standards specific to DUT group. While there are so many differences in all these standards, this table gives us a simple summary of their respective test methodology. What is common in this group is mainly the conducted EMI as well as the radiated EMI. Hence, in this session, we will look more into EMI testing. Next, we look into the setup and tools regarding this measurement. Within a system configuration, there will be a device or equipment under test. A transducer is used to convert the conducted or radiated energy for the EMI test receiver. A conducted measurement will usually need a listen or absorbing clamp, while radiated measurement uses antenna. Here's a typical compliance radiated emission setup. Usually a chamber is used to reduce environmental noise. The chamber size depends on both CISPR standard requirement as well as the DUT size. The test usually requires a turntable to rotate the device and a switching unit to control the antenna position and orientation. On the other side of the chamber, a software tool is usually used to automate the whole setup, capturing data from a connected EMI receiver to tabulate into a report. In a compliance conducted emission test, the requirement will involve a reference plane at a certain height. Then a line impedance stabilizing network, LISN, provide the power to the EUT. Some will be able to couple the noise from the EUT for test receiver measurement. Else, a current absorbing clamp is used. In this setup, the standards also specify the requirement for transducer to be sensitive enough to pick up the required interference. Radiated emission will be on the antenna requirement, while the conducted will be on the listen and clamps. One of the more critical ones for conducted measurement is the listen. Its purpose is mainly to stabilize the power provided to the DUT. On the other hand, it also couples the noise generated in the power line due to DUT to the EMI receiver. Standards will often characterize the listen requirement based on different product group. Selecting the right tool is crucial to the measurement. For full compliance measurement, EMI receiver will indicate which standard they are compliant to. There are also a selection of tools available for pre-compliant test equipment which they may lack the full sensitivity as required by the CISPR standard. Then, we also have spectrum analyzer which is able to provide some pre-compliant measurement. The measurement mechanism is slightly different from the receiver, but they are still able to give a good reference for the measurements. Going below pre-compliant, there's also an arsenal of diagnostic equipment like scopes and handheld spectrum that allow users to correlate EMI measurements to their DUT characteristic. They typically do not include CISPR limit lines because they are really meant for general RF and time domain measurements. One key characteristic often mentioned in receiver testing is the quasi-peak detector. Unlike peak detector that captures the highest measured signal, quasi-peak detector acts like a lossy filter, which is closer to how a listener can experience interference in real life. These detectors usually can only be found in EMI receiver, which is not available in general spectrum analyzer or scope. When we come into consideration of what equipment is suitable, this is a good table to understand the features that are related to typical CISPR standard measurement. Auto-ranging is only available in EMI receiver. Some spectrum analyzer with the right options can also provide EMI detectors measurement. The measurement mechanism between equipment are also different. For example, sensitivity of scope will not match EMI or spectrum analyzer as it is a wideband measurement. Receiver and spectrum analyzer will perform frequency selected scanning, which help reduce the wideband noise. Lastly, receiver usually can only be found in EMC test lab. Spectrum analyzer are more found in pre-compliance setup, and scopes are more common in R&D lab for general testing. Having said so, we can also consider about the journey from design to prototype to manufacturing phases. Most users will only focus on compliance measurement when the product is closer to the production testing. Before that, some pre-compliance and debugging can usually be done on prototype product using scopes or spectrum analyzer. Simulation would be something useful to predict what emission can be. In terms of preventive measures that can be done to fix EMI problem, in earlier phases is definitely more cost effective. If the user only found EMC problem close to manufacturing phase, the need to change hardware, respin the design will definitely incur more cost. Hence, this is why we want to shift the EMI testing focus to be as early as possible. Debugging EMC problem with oscilloscope is not a new topic. There have been many publications focusing on near-field measurement with modern oscilloscope. Why we like to promote on using scope is mainly because it is a really commonly available equipment on every engineer's desk. Through FFT, a scope provides both time and frequency domain perspective and allow us to see both at the same time. In older scope technology, FFT is done by acquiring a duration of sample, applying a window filter to reduce the spectral leakage, followed by software to process on the FFT, then using zoom to display the required FFT result. The problem, as limited by technology of its time, created a slow response that made FFT measurement unfriendly. In RNS new oscilloscope, a digital down conversion is used to reduce the sample required and just the required range. The reduced sample are then passed into hardware ASIC that allow an even faster processing, hence this improves the overall usability of the FFT, especially in EMI testing. Here's a spectral measurement done on the RTM 3000. On the top of the screen is a time domain waveform where we can see the trigger and the noise chirp. At the bottom is the current FFT result, and spectrogram in the middle records all the previous spectral magnitude. A simple to use start, stop and RBW setting make configuring the FFT easier. A color coded helps to indicate spectral magnitude, and a dB microvolt scaling similar to EMI measurement. And lastly, the waterfall spectrogram shows previous emissions that are recorded. While not all scopes are created equal, do look into the needed features that will help with your EMI measurement. For example, some scopes provide mask testing, while others can even provide frequency zone triggering. Now, what is the concern for switchboard power supply for EMC? In terms of power integrity, a noisy power supply can emit noise in various ways through capacitive coupling, inductor stored energy, large current loop around the circuit board, galvanic coupling at different regions, and common mode noise that can be radiated. This noise often coupled through the power plane on circuit board and will appear in the form of noise ripple that can highly impact the performance. For example, if we provide a noisy power to the clock chip, the noise will propagate through and induce jitter to the clock. The jitterish clock and the noise power are also provided to different chipsets that will further degrade the performance. Even in RF circuit, a noisy power supply will not only introduce its noise, it can further intermodulate with the signal to create higher sideband noise. For better efficiency, switch mode power supply is moving towards faster switching technology using gallium nitride and silicon carbide. This will be a challenging technology in EMC because with the faster switching, it will definitely introduce more harmonics into the circuit. Let's go through a few case studies on the power supply noises and how to do the measurement. First is an example from Graz University of Technology in Austria, where they are interested on optimizing a wide bandgap switching. In their circuit, they included a variable resistor to control the switching slew rate. Based on our measurement with near-field probe and a high-voltage differential probe, we can compare the emissions on a fast-gate driver signal and compare that to a shape-gated driver signal. Through scope with FFT, we can easily observe the improvement in emission and in which frequency range. In the next case study, we look at the conductor emission setup to compare a receiver and a scope FFT measurement. A receiver provides a compliance measurement fulfilling the measurement time, detector configuration as per CISPR standards. It also provides a limit line for the measurement. If we were to debug this in a pre-compliance setup, a scope can also recreate a similar result to identify key emissions frequency. While the scope lacks in sensitivity and dynamic range, it makes up by being easily available in the lab for R&D to perform pre-compliant and verifications for debugging. Coming to the demo part, as you can see, my setup here consists of a power supply, a spectrum analyzer, and a scope. Then of course, there are accessories like listen, filter kit, and DUT. We will try out the measurement with a listen for conductor measurement. Before we start, let's understand a little more on the DUT that we are testing on. It is a simple buck converter switch mode power supply that will take an input of 8 to 16 volt and providing 5 volt as output. The buck converter is built with an input filter. After the filter, the power input will be controlled by a MOSFET switch. We can look into the gate signal and output at switch node. The gate signal is controlled by a non-synchronous voltage mode controller. There's an RC input for switching frequency control. With the controller, a feedback and compensation path provide the necessary adjustment to the gate driver. A current injection point is also available if you want to look at the body plot of the feedback loop. The DUT also has a constant load and dynamic load controlled by a low side gate driver to simulate load changes. For this demo, we will use mostly on the constant load. In this experiment, we are also using a listen from EMV Lange, the NNB21. It offers a 50 ohm, 10 amp connection and capable to tap out the conductor emissions from DUT side for measurement up to 1 GHz. The key for this experiment is the WÜRTH filter design kit. It allows us to experiment on how different component insertion loss can help reduce specific emission. The filter design kit will be put between the listen and the DUT. This way, we can experiment different filter parts affecting the emission result. The final conductor emission setup will look like this. You should have noticed I placed the setup on the conductive plane. The reason being, to be as close to a compliance setup will help us to correlate our result with the compliance lab. Then we have a scope and spectrum analyzer for measurement comparison. The power supply will provide an 8 to 12 volt to the listen. Then, the listen filter and provide the isolation to the DUT, while the WÜRTH filter kit will allow us to experiment on different components. The scope and spectrum will then pick up the conductor emissions for measurement. Let's start with a baseline noise measurement. Before we start, remember to turn off the power output, then connect all the devices together. Here, we'll use a direct connection over the common mode choke socket and tap into the DUT after the filter block. To set up the instrument is not that straightforward. The listen RF output has a 10 dB attenuation and a 50 ohm coupling. On scope, Set the coupling to 50 ohm. Add a user-defined ratio of 3.162:1. Change channel scale to the most sensitive before clipping and turn on FFT. And FFT start at 0 Hz, stop at 1 GHz with RBW of 200 kHz. Set the vertical unit to dB microvolt with the reference level of 60 dB microvolt and a range of 50 dB. Then, turn on max hold. Set trigger to free run or with the smaller sensitivity. On spectrum, spectrums are 50 ohms by default. Stop at 1 GHz with RBW of 200 kHz. Add an attenuation of 10 dB in the amplitude value. Set the vertical unit to dB microvolt and a range of 50 dB. With the reference level of 60 dB microvolt. Then, turn on max hold. If we compare the result from the two devices, they are quite similar. The RTM, although lacking in sensitivity and dynamic range, it still picks up the crucial emissions as the FPC 1500. The FPC uses a slower detection for better accuracy, where the scope makes up with a more dynamic response. With a higher performance instrument, you will see a boost in measurement speed and accuracy. Yet, they are still picking up very similar spectrum nature. Next, we try with different components. One with a 1 mH common mode choke, then with 20 mH common mode choke. We can also add 150 nanofarad X-cap to change the filter profile. With different components, they will provide different insertion loss at different frequency. We can study the specifications as provided by the WÜRTH kit to help us to design a better filter to eliminate the emissions that is not wanted in the design. In summary, switch mode power supply has big impact on EMI if not designed carefully. Noise can propagate through the circuits and affect its performance. If we delay the testing of EMC at the late stages of design, we may face bigger challenges. While lab equipment like scope and mid-range spectrum analyzer may not meet the CISPR required specification for EMI measurement, they do provide a glimpse into the EMC performance and allow us to make early detection and debugging. I hope this lesson is useful. For more information, please follow the RNS website. Thank you.